Thanks, Srikanth, for inviting me for this talk. And in a Wi-Fi Knowledge Summit, we are talking about UWB, so that tells me that UWB is gaining some attention. Okay, so let's talk about UWB. So UWB, which stands for ultra-wideband, it solves a problem that does not have or did not have a robust solution, and that is precise localization. So how precise does it get us? It gets us to centimeter level precision. Why do we need that kind of a precision? So if we want to estimate the distance between two devices, we can estimate down to centimeter level. Do we need that? Why do we need that? I mean, so for example, when I am at home, I don't want all my devices to be locked. And the only option that Android provides me is connect to the Wi-Fi AP, and as long as you are connected to the Wi-Fi AP, your devices are unlocked. But if I go outside my home, it's still connected to my Wi-Fi. So it's not really a robust solution. So if you have a device that you want to be unlocked, if you have maybe your car that needs to be unlocked, if you have your home that needs to be unlocked, then you need to have your authorized device to have a very precise distance measured between the device that needs to be unlocked and your authorized device. So if I'm carrying a phone or if I'm carrying a watch, and if I'm walking around and I want my, say for example, car to unlock itself as I go closer to it, it needs to know precisely how far I am from the car. I don't want my car to be unlocked when I am like 10 meters away, right? So then somebody else can just get into the car and drive away. So the same thing with home. I want my home door to be unlocked only when I am close by. And the door needs to know whether I am inside the door or outside the door, right? So it needs to be quite precise, the distance measurement. And that's what ultra-wideband allows us to do. It also enables point-to-point communication. So unlike Wi-Fi, where the access point needs to control or initiate all the distance measurements, here any device can act as a controller, and it can communicate to all the other ultra-wideband enabled devices. So in a home, you can have your phone acting as a controller, and it can estimate the distance of each of the other ultra-wideband enabled devices in home. Okay, and as the name indicates, ultra-wideband uses at least 500 megahertz bandwidth. So you need to be more than 500 megahertz bandwidth to qualify as an ultra-wideband device. And because we use such a large bandwidth, there are strict regulations that are associated with being an ultra-wideband device. We are not allowed to transmit beyond a power spectral density of minus 41.3 dBm per megahertz, which is, if you compare that to Wi-Fi or Bluetooth, it's way lower. So most of the times, because we transmit at such a low power, the received signal is always below the noise floor of our receiver. And because we operate at such large bandwidth, right, all the other wireless signals, the Bluetooth or the wireless LAN, they all look like narrowband interferers to us. So we can ignore them because they don't really destroy the ultra-wideband signal. Even though they are at a much higher power, they are still narrowband interferers, and I can put a bandpass filter and get rid of them. So it's very robust in terms of interference from other wireless technologies. And also because it is quite low power, it does not really interfere so much with wireless LAN or Bluetooth or cellular because of the very low power that we transmit. And the physical layer itself, the physical layer is very different. It's way different from all the other physical layers that we are used to, and that is used in a very advantageous way with ultra-wideband. It uses something called the impulse radio, which means we send a short pulse, which is 2 nanoseconds wide, and we send a series of these pulses. When I first got into ultra-wideband, I learned about, okay, we are going to communicate via these pulses, and At that time, I was reading up on the quantum computers, and this is how you actually control the quantum computers. You send this very small pulses. And we do something similar here, but anyway, that's a different topic. But this is actually called impulse radio, where we send this 2 nanosecond pulses, and the 500 megahertz bandwidth is basically coming from this very short pulses that we send. The physical layer frame format is very similar to any other packet-based wireless system. So just like wireless LAN, you have this short training sequence, long training sequence, and then the header and the payload. Here you have a preamble that is used for synchronization and channel estimation, and then you have a sequence called STS, which is a cryptographically secure sequence that is generated with 128 or 256-bit AES encryption, and it's kind of a security feature that's built into physical layer. Again, to make sure that the distance measurement that we achieve with ultra-wideband cannot be spoofed or cannot be tricked with the man-in-the-middle attacks, somebody else coming in and then tricking the receiver into estimating a smaller distance. So it's kind of a security feature that's built in. So it's ultra-wideband allows for secure ranging, not just ranging. And then we have the header, the PHY header and the payload. So in addition to providing this ranging capability, it also allows for payload transmission at the same time. Okay, so how do we estimate the distance? Again, one of the simplest ways or rudimentary ways of estimating the distance, which I think the previous speaker also talked about, was using RSSI. Every receiver measures the received power, and you can then say if the transmit power is held constant, you know that the path loss is then the transmit power minus the received power, and path loss is related to distance. The farther you are, then the higher your path loss is. So the path loss can be mapped to a distance. But it's a very unreliable way of really estimating your distance, because the RSSI changes based on several factors. First, the transmit power changes from device to device. It changes if the device is hot or whether it is cold. The multipath situations, there is interference, all of this change RSSI. So it's a very unreliable way of doing this. Then Bluetooth has this HADM, this is a high accuracy distance measurement feature that's added to the 5.3 standard. And what this does is use, after the packet tones are sent, and where the phase is then, the phase difference between the tone from transmitter to receiver is then measured, and that is then mapped to a distance value. This is not an easy thing to do because there are a lot of details that we need to take care of here. First, we don't know, the receiver does not know what is the phase at which the transmit tone is being sent, because the phase changes as it goes through the baud trace, and it goes through the antenna, the phase changes. So it needs precise calibration to even know what is the phase of the transmitter. And then the phase difference wraps around, because every time you go beyond half a wavelength, the phase wraps around. So any distance estimation that's based on phase cannot happen with just one frequency. To resolve that wraparound, you need multiple frequencies. So it's a very complicated signal processing that you need to do at the receiver to be able to really estimate the distance. And you can go and watch YouTube videos of how good the Bluetooth HADM-based distance estimation is, and it's not any better than the Wi-Fi results that we have seen. So it's half a meter, 1 meter. It's usually 1 meter, and it's very slow because there is a lot of averaging that's being done. And then the other way is estimating it by estimating the time of flight, or which is the round trip time, which again we heard about in the last presentation. And that's what we will talk about next. Again, one of our use cases is secure access, right? So you have an authorized device, and you want the authorized device to be able to access something, to unlock your car, or to get access to another, a car or home. And so the way to do that is that you estimate the distance and the access is granted to you only when you are close enough. So one of our key use cases is is accessing the car without a specific device that's custom made for the car. So we have, say, a phone or a key fob that's now sending a poll message to the car, and the car is then sending a response back. So the round trip time is basically, you have a time that has elapsed here at the initiator side, you have a time that has elapsed at the responder side, and there are 2 times the time of flight, so you can basically calculate the time of flight in this simple way, right? And that's all that is done in ranging. This is called the single-sided two-way ranging because here only the initiator can estimate the time of flight. If you do a double-sided two-way ranging, then 2 more messages are being sent, and the responder can also estimate the time of flight. So, because we heard that the wireless LAN can also do round-trip time-based distance estimation. So how does ultra-wideband really help? What is the advantage that the ultra-wideband provides? A typical channel impulse response is shown here in this plot here. So we are transmitting short pulses, right? And that's a big advantage. Because we are transmitting short pulses that are only 2 nanoseconds wide, we can resolve multipath components a lot better. So if you have a multipath channel, and because we are essentially measuring the channel impulse response, so this is the channel impulse response, a typical channel impulse response. So in a line of sight scenario, there is no problem because there is only one strong path. But in a multipath scenario, when you have a lot of reflections that are coming back to you, what is important is to find out what is the first shortest path that we have. And because of the very short width that we have for the ultra-wideband pulses, we can estimate what is the shortest path. So if you have a path that's right here, so let's say this is the main path in line of sight scenario. And then in a multipath scenario, you have a main path that's maybe 15 dB lower than the strongest path because the reflection is stronger. And if you have a main path here, if you have the first path here, and then you have a main path here, and if you cannot estimate what is at 825 nanoseconds, and if you go and estimate the strongest one, then you already make several nanoseconds of error in your time of flight estimation. And 1 nanosecond corresponds to 30 centimeters because it's the time, it's the speed of light times the time. So if you make 10 nanosecond error, that translates to 3 meter distance error, right? So the short pulse widths of ultra-wideband really help here. It's not just with the multipath resolution, but you cannot estimate the angle of arrival. So you have a transmission coming from somewhere. You cannot estimate the angle of arrival precisely if you have multiple paths overlapping with each other. They are superimposing with each other. So you have a line of sight component that's coming in different angle, and you have a reflection that is coming from a different angle. So unless you can resolve these 2 paths separately, you cannot estimate the angle of arrival, right? And that is another key advantage that ultra-wideband provides. And that is illustrated here. So you have a direct path that's coming straight here, and because there is a wall, it's attenuated quite heavily. But you have reflections, so you have these 2 reflections here. Now, for a narrowband system, if you don't have a bandwidth that's wide enough, then the narrowband system has a time domain signal that's wider. And because the time domain signal is wider, all of these signals are then overlapping with each other. And then we cannot resolve what is the first path, we cannot resolve the angle because you have multiple signals overlapping. Whereas on an ultra-wideband system, because you have this really short pulse, you can basically resolve the first path with the reflected path, and that really helps not just in being very precise, but also in being able to estimate the angle of arrival. And the precision, how good you are in resolving multipath is basically just a function of bandwidth. It's nothing else, right? And as we increase the wireless LAN bandwidth, of course, we can also do better accuracy in terms of distance estimation. So you can, right now the Wi-Fi systems are here. Already we are struggling to find 160 megahertz bandwidth for Wi-Fi operation. We are mostly stuck with 80, and maybe 320 megahertz, but will we really get 320 megahertz whenever we want to do? That's questionable. This is where Wi-Fi is, and this is where ultra-wideband is currently. So it's an order of magnitude better than what we can do with Wi-Fi today. So with wireless LAN or Bluetooth, this is the uncertainty that we have in our distance measurement, the gray area. With ultra-wideband, the uncertainty is smaller, which means the accuracy is better. But it's not just that. We can estimate also the angle of arrival and do the 2D positioning, and that's a big advantage. So this is what we can do. This is, again, what we are doing already now in practice with, I think the previous speaker was not measuring the ultra-wideband performance on Samsung phone. So that's probably is going to give much better results, because most of the Samsung phones have ultra-wideband now. So we can do plus or minus 10 centimeter distance, plus or minus 3 degree angle of arrival. And in line of sight conditions, the link budget is more or less the same as Wi-Fi. We can do 100 meters of transmission and reception. We are quite robust to multipath and also quite robust to interference, because we are wideband, and all the other wireless systems look like narrowband to us. The security is built into physical layer, and then because we are sending these short pulses, the frame duration is quite short. It's 100 microseconds or thereabouts, and we can therefore have latencies that are less than 10 milliseconds. So where do we want to go from? We want to go from on what we have on the left, what we have today, where car manufacturers also give you a key fob, which is a proprietary implementation. So and it's easily hackable. We can just you can see videos of people hacking this with just a really long antenna. So it's easy to hack. So we want to go from here to here, where we are all carrying around pocket computers, and it has all the wireless technologies already built in. So we want to, I have time? Okay. So we have, we want to use the phone as the key, and that's what we want to basically achieve with ultra-wideband. And ultra-wideband doesn't work standalone. It still uses the Bluetooth that we have to communicate all the configurations that we need to communicate between two devices. So the key and all the key that needs to be used for encryption, whatever else that we need to configure, all of this is happening over Bluetooth, and then there is a handover to the ultra-wideband physical layer, and then the secure ranging happens, and everything else goes on from that. So we have all of these big companies working together to really bring this to the cars that we will buy soon in the future, in the near future. And this is not just the car access use case, but also we have a lot of, so for example, indoor positioning, where we are in an airport or a shopping mall, and we want precise positioning there. We want to maybe use ultra-wideband just like we use GPS outside. Right? And that is one of the use cases. There are a lot of these use cases here. There is even the social distancing use case, because somebody made this during COVID, I suppose. So you can use this for ticket validation. So you buy a metro ticket, the metro ticket is on your phone. You just walk into the metro, and you don't need to stop anywhere. The gate just automatically opens, because it automatically authenticates that you have a ticket on the phone. So you can use it for mobile payment. You can use it as a remote control. You have a TV, or you can point and trigger, because you have this 2D positioning along with the angle of arrival. And then you have, of course, access control for the car, access control for the home. So all of these are use cases. The car consortium is specific to the automotive segment, and then this is specific to the all the other segments or all the other use cases. So again, a lot of companies are coming together to really standardize what we can do with the protocols, what we can do with the ultra-wideband, and how do we build all these use cases with ultra-wideband. So market segments where ultra-wideband is gaining interest is, we have the mobiles where we have wearables, we have phones, we have laptops, and then we have the automotive markets, the cars and scooters, and then we have the IoT segment. So we put this in AZs, in TVs, in thermostats, right, in lights. And there is also a lot of industrial use cases where you can use this for asset tracking, you can use it for inventory management, right? So there is ultra-wide potential, and we have a lot of these companies coming together to build this ecosystem. So yeah, that's been my time. Thanks.
Yeah, stay on. Yeah, we have time for questions, Sanjeev, Mike. Yeah.
Thank you so much. That was a nice presentation. We did talk about Bluetooth versus UWB. I'm from automotive, so we have used this. I have one question. We have been recently talking about the audio streaming use cases of Bluetooth. And can I use UWB? There was a bit of fuss in between. Can you throw some light on that?
Yeah, I mean, we are also thinking about, it's one of the active engagements that we are having. We are trying to use UWB for audio streaming. The newer versions of the standard is also increasing the data rate, so it is one of the potential use cases, yes.
Any ballpark number on the current data rate that you're supporting for the audio streaming over UWB? Let's say SBC over Bluetooth is 330 kbits per second. So how much would it be over ultra-wideband?
I think the 64 kilobits per second is not a problem. It's
64
possible.
Is what you're saying.
It's already possible today.
Okay.
I mean, there is no limitation in terms of, it's just, if we continuously use the airtime, then we would be blocking other devices, other ultra-wideband devices. Mm-hmm. So it's mostly a coexistence of ultra-wideband devices that needs to be looked into.
Okay. Yeah, so there is a focus on that. It's good to know. Thanks.
Yeah. Vijay?
Yeah. So in indoor locationing, multipath is a huge issue, right? And what we have observed is that large channel width results or it magnifies the problem because of large delay spread. So is there anything specific that you do to negate that multipath effect or?
Yeah, I mean, it's basically because of the short pulse width that we have. It's possible to find out what is the first instance at which you have your first path. That's basically the key.
Okay, so you do the lowest path.
Shortest path.
Identify the lowest path.
Identify the lowest path. Yeah.
Okay. Yeah.
I have a question, something related to that. What is the delay spread? Because in one of the slide you showed the CIR plot. So I was eager to know what is the typical range of this delay spread in a UWB channel.
I mean, there are channel models. There is office n-loss channel models. I haven't really looked at the delay spread numbers, so I'm not sure. But it is a office.
Sub 50 nanoseconds, I think, typically. 50 nanoseconds to 100 nanoseconds.
Something like that.
Yeah. RMS.
I think the difference between what Wi-Fi does and what UWB does is the waveform that is used, right? 11AZ, 11MC still uses OFDMA waveform. The LTS is sent and that is used for correlation. It's still the OFDM waveform which is still susceptible to the delay spread. It is not the case with UWB. It's pulses and you correlate the pulses, right? I think the waveform itself makes a difference. Is that right?
So just to add, because I know the Wi-Fi, see, as far as the locking onto the time, it's the preamble. So the preamble is you can generate it using an OFDM transmitter, but it's independently defined. So I've looked at the sequence there as well. They are comparable, but not equal, but they're comparable. So the data transmission aspects are different, but what is used for timing estimation is the preamble. So you don't necessarily get into OFDM nitty-gritties. Okay? So I think, thanks, Prasanna.